Okay, so let's continue. The new topic for today's lecture is red-black tree. Well, this is really a hard topic, to be honest. And I remember once I talked to a senior professor saying, I'm going to cover red-black trees in my 532, and he said, if you can do that, I'm surprised. So, well, let me try that. So, but before we move on, before we really talk about the red-black tree, I need to remind you that red-black tree is a mutation or a updated, fancier version of binary search tree. So it has all the properties that the binary search trees have, but with more fancy way to keep the tree balanced. So, well, before we move on, let's have a very quick review on what is the binary search tree. So this video will be only a review session. And if you believe you remember everything about the binary search tree, feel free to skip this video. So, excuse me. So for a binary search tree, each of the node should have at least those things. So it should have a key, and then a left pointer to the left child, and then a right pointer to the right child, and a p, which is a pointer to the parent. So if we have a node and it knows the left child, the right child, and also the parent. So, well, for the binary search tree, the important property is the key of the parent should be greater or equal to the key of the left child, and it should be small or equal to the key of the right child. So this is the binary search tree property. If you have a binary search tree, this property should be true for all the subtrees. And if you have an AVL tree or a red-black tree, which is what we are going to cover later, this property should also be true. So after we have a binary search tree, then well, one of the very cool thing we can do is we can do a tree walk, and we are going to focus on the in-order tree walk, which is if you are visiting a tree, you can visit the left subtree first, and then the root, and then the right subtree. So if you are visiting all the nodes following this way, and you are doing a in-order tree walk, and you can also do a pre-order tree walk or a post-order tree walk. The next thing, well, if you want to do a search, we want to search using a key. So in this case, what the process should be, we visit a node, and then we want to compare the current key on the current node with the key we are looking for. If we're lucky enough, we find that, and then we return the current value. Otherwise, we have to make a decision. Do we want to search the left subtree, or do we want to search the right subtree? So this is the first solution. We can do a recursive tree search. And next thing, we can also do a iterative tree search. So for those two solutions, the thinking, the methodology are exactly the same. We make a comparison to the root if it's not the value we are looking for, and then we make a decision. Do we want to search in the left subtree, or do we want to search the right subtree? So we have two different versions of doing tree searches. So the next thing, if you want to do a insert, so for insertion, the process is similar. So we want to use the current value we want to insert and then compare with the root. And based on the comparison result, we make the decision. Should this value be inserted to the left subtree or the right subtree? And then we go to that subtree, we do this kind of comparison again. So we are going to continue trace down the subtree until we find a slot which is empty, which is a null or a none, saying the current node has no left child or no right child, and then I'm going to insert the new value there. So like a search, if we want to consider to do a insertion, and then the time complexity will be the OH, and H is the height of the tree. So we have to go all the way down. And the worst case, we are inserting the new value in the deepest level of the leaf. And then that will be the OH. So next thing, sorting. So sorting with the binary search tree is possible. And the reason is after we have a binary search tree, and if we want to do a in-order tree walk and print all the keys, and you will see we are printing all the key values from small to large. So in other words, we are getting all the keys sorted. So with a binary search tree, it is possible to do a sorting, but it's not so impressive. Well, we have analyzed that, so the best case it is omega n log n. So why? Because it is a comparison sorting. So if we build a binary search tree and then do a in-order tree walk, this data structure is built 100% based on comparisons. So since it is a comparison sort, well, it is omega n log n. And in the worst case, it's going to be a O n square. And if you remember, the worst case of a binary search tree will be we always insert the value on one side. So if we start from here and then we grow the tree on one side, one side, one side. So if we continue growing the tree this way, so eventually you will find that the tree is just a linear structure. So I would say even though we are using the binary search tree, it is really a linked list. Okay, so other operations. Well, if you want to find the minimum, and the minimum of the binary search tree should be the roots left child, left child, left child, left child, left child. So you want to go all the way to the left side until there's no more space to go, and then you can grab the minimum. So that is easy, and you can do the maximum in a similar way. So instead of always going to the left side, and you can always go to the right side. The next thing, successor. Successor is very important. So if you have a node and if you want to know what is the successor of that node, and the rule is if the current node X has a right subtree, and then the successor will be the minimum of the right subtree. And otherwise, if X has no right subtree and the successor is the first ancestor of the X whose left child is also an ancestor of X. So that is the algorithm for the successor, and we are gonna mainly using the first case, so which is this case. So this is the case we are gonna use when we want to do deletions. So the next part, deletion, the really hard part. So there are three possible cases. The first case, probably the easiest one. So if X has no children, and then we just throw away the node. So let me give you the example here. So if we want to delete the node K, you can see node K has no children. Otherwise, this node K itself is a leaf. So if you want to delete a leaf, you just throw that away and telling the parent H, saying, hey, from now on you have no right child K anymore. So just detach the K from the H and then throw away the node K, and then the first case is done. So that's the first case. The second case, if X has one child, so for example H. Okay, so if we want to delete H and then we want to consider the direct child, which is also the only child K. So after H is thrown away, and then we want to attach K directly to F as F's right child. So if we do that, and then we just skip the H and then link K directly to F. So K is going to be linked directly to F. And in this case, well, K will be F's right child, and then we say we splice out the node H. So the next thing, the really hard part. So if x has no children, has two children. So if x has two children, we want to swap x with the successor. And after we swap the x with the successor, x will be at the new location. And then we delete x at the new location. So one of the example is if you want to delete b. So b has both children. So how should we delete it? The first thing is that we want to figure out what is b's successor. So if we go back, so the successor algorithm is here. So if x has a right subtree, and then successor is the minimum node of the right subtree. Okay, so that is the definition of successor. And if we go back here, so b's successor will be the subtree dc's minimum. So if we visit the subtree of the d and c, the minimum is the c, right? Okay, so if we want to do the first step, swap x with the successor. So what will happen will be like this. Let me write here. So if you want to swap the b with the successor, and then the new value here will be c, and b will be swapped here. Sorry for my handwriting. That's really awful. Okay, so this is the first step. So we are swapping the b with the successor c. Okay, so that's the first step. And then, well, the node we are trying to delete, which is b, is now moved to the new location here. And we also want to delete this new node from the new location. So b is now here, and if we want to delete b, now we come back to case number 1, which is the current node b, which is here, has no children. So we just throw that away. So eventually the next step will be we are gonna throw the b away from the new location, and then b is deleted. So after we delete the b, and then the successor c will take the location of the previous location of the b. So you can see c will be here, and then c is smaller than f, and then c is greater than a, c is smaller than d. So this is still a valid binary search tree. So that is the review part of the binary search tree, and I will see you in the next video.